Thank you all for joining. Good morning, good afternoon, good evening. Welcome to this 5th edition of the Great Designs in Steel Technical Webinars. My name is Brian Esterberg. I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. And today we're pleased to welcome Dr. Jun Hu, Senior Product Research Engineer from Cleveland Cliffs Research and Innovation Center. Today's presentation is a comparison of 1500 megapascal ultra-high-strength steels for automotive applications. So let's get to it. Your microphones have been muted. Please use the Q&A feature throughout today's presentation to submit questions. We will not be utilizing the chat or raised hand feature. Again, please use the Q&A feature to submit questions. And my colleague, Dr. Hisham Aizat, our Senior Technical Advisor, will join us to address questions following the presentation. A recording of this presentation is the slides and the recording will be available on demand, at autosteel.org following today's webinar. So with that, it's my pleasure to welcome Dr. Jun Hu.
All right, morning everyone. This is Jun Hu from Cleveland Cliffs. Today is my great honor to present this topic in the GDIS webinar. So before the beginning, like always, this is a team effort. So I would like to always thank my team members and management for the support. I would like to also acknowledge Brian and Hisham for all the coordinations. So let's start from here. First of all, as we all know that the automotive OEMs always want to build their cars of higher safety, lighter weight, and lower cost. And to satisfy all these needs as a material supplier, Cleveland Cliffs offers all kinds of advanced high-strength steels to ultra-high-strength steels. And as we can see here, at lower strength level, we can still have all kinds of different microstructure combinations grades. But if we move on to higher strength, we have no other options but only martensite grades. And in today's talk, we will basically only focus on the 1500 grades. And talking about this category, based on our catalog, we're actually talking about two cold forming grades, the martensite 1500 and dual phase 1470, and one hot forming grade, press hardening steel 1500. And for the martensite, as shown by its basically name, it is mainly supplied to the cold rolling lines. As a comparison, the DP was basically designed to exhibit a little bit better formability to allow it to also be processed in the conventional cold stamping lines. As for the PHS, as shown by its name, basically, it is mainly supplied to the hot stamping lines, as shown in the animation. But in some cases, it can also be processed through the roll forming lines to the tubular components, and then heat treated and fully quenched to be martensite. And eventually, all of these 1500 grades will be manufactured to the top critical structures in the automotive. For example, the cross members, the reinforcements beams, ABC pillars, and bumpers, and so on. And more important thing is in the protection of electrical vehicles, as we can see here, basically the 1500 grades can play a very important role in not only something like the battery tray or the rocker reinforcement structures, as we can see in the examples. And the most important thing here is that the steel structures can perform much better fracture resistance in something like the 3-point bending scenarios than the extruded aluminum alloy structures, which are used in the current EV designs, as we can see on the right-hand side. Of course, for these applications, if you're interested in more details, please feel free to visit our website or directly contact our application engineering group. So back to the materials. We have learned that the 1500 grades are very important and promising in the automotive applications. So the following question is very natural, which is what are the differences among all these 1500 grades? And that is the scope of this work. And we conducted some comparative studies based on their mechanical properties. And here we can further divide it, the contents to two parts. In the first part, we will only focus on the two cold forming grades, the martensitic 1500 versus the dual phase 1470. One of them is single phase, the other one is dual phase. One of them exhibit better formability, the other one exhibit better fracture resistance. And we hope this kind of comparison can inspire our future ultra-high-strength steel microstructure design strategies. As for the second part, basically, we would like to expand our comparison parameter a little bit larger to also include some hot forming grades, not only the PHS, but also the aluminum alloy 7075 T6. And we'll mainly focus on their ductility in the crash scenarios. And it's also a good chance to basically compare the steels versus aluminum alloy. And the basic idea of this comparison is to provide a general idea to our automotive customers in their future material selection considerations. So now we can move on to the first part of our study, which is the two co-forming grades. So let's first check their microstructures. And as we can see that on the right-hand side, some ferrite islands in the middle of the martensite matrix. And other than these 10% ferrite, all the rest aspects are similarities. And so it's very good to compare these two. And in the comparison, we'll start from comparing their strength, especially their strength change after the pan baking treatment. And here we can basically consider their microstructures first. As we know that the martensite in both grades are the main source of the strength. Therefore, the single martensitic phase should provide more strength. So based on this, we can basically predict that it's very likely the martensitic should perform better than DP after the pan baking cycles. Of course, here we assume that the pan baking cycles can 100% perform the effects on the parts made of these materials. As for the testing procedure, it is basically highly simplified based on the actual automotive manufacturing process. Briefly speaking, the steps start from pre-straining the samples to some extent to accumulate some dislocations in the microstructure. And then we'll bake the tensile coupons in the furnace to allow the interstitial atoms, such as carbons or nitrogens, to basically gather around the dislocations to pin them together, like something called the cultural atmosphere, to pin them in the following reloading. And in the reloading, to basically get rid of this pinning, the material will exhibit elevated yield strength, as we can see in the diagram. So there are some other keynotes that we refer to, but not completely follow the standards. For example, basically we pre-strand the samples at 4 pre-strand levels and bake them at basically one condition. And of course, there are multiple mechanisms, and the primary one is the cultural atmosphere. And the most important thing is that we calculate the stress based on the engineering stress formula. So here we can see the results. First of all, as we can see the stress and curves of both materials, and both of them exhibit obvious yield strength elevation after pre-straining and baking. Even without pre-straining, both materials exhibit some yield strength elevation. And of course, without pre-straining, this kind of elevation on the yield are caused by the stress relief. And also we can see that with the increasing of the pre-strain levels, both materials also exhibit more yield strength elevation. But if we basically extract the elevation results and plot them together, we can see that on the right-hand side, at all the pre-strain levels, the martensitic exhibit more yield strength elevation than the DP. This is exactly as we expected because the ferrite in the DP basically lower down the strength change after the treatment. And then we can move on to the ductility side and start from the formability. And similar to the previous section, let's first think about the microstructure. As we know, as we already talked about that in the DP, our developers basically retain some ferrite to be the source of more ductility to allow the DP to be able to go through the conventional cold stamping lines. And of course, here we have to say that this type of enhanced formability is only one type of this formability concept, which we call it the global formability, and represents the necking resistance of the material. So since we have the global, now we must also have the local formability. So of course, for the global formability, because of the ferrite, the DP should exhibit better than martensite. So back to the local formability, it basically, based on some representative literatures we listed here, it is primarily caused by the microhardness difference in the microstructure between the hard and soft faces. In this case, of course, is martensite and ferrite. And the local formability basically represents the fracture resistance. And of course, because of the existence of the ferrite in the DP, we can predict that very likely the single phase martensitic should be better than DP on this aspect. So then in the following slides, we will see a series of formability testings. And here we adopted some most basic and standardized testing. We tested the tensile, the uniaxial tension. We tested the forming limit curves, the Hooke expansion ratios, and local bending angles. And also we expanded a little bit, especially on the tensile results. And here we used our proposed hybrid methods to measure the fracture strength to represent the local formability here. Briefly speaking, for this hybrid method, we used the DIC to measure the two planar strength components from beginning all the way to fracture. And then based on the fractured samples, we use a laser scanning microscope to measure the thickness strand at fracture. And altogether, regardless of some kind of synchronization errors, we can use the von Mises effective strand formula to derive the fracture strand to represent the local formability. Here, as always, we would like to always emphasize that the fracture strand is not equal to tensile elongation. They represent two different aspects, two different types of formability. As for the results, let's first look at the global formability. First is the stress strain curves of these two materials in this diagram. And we basically plotted all the repeated tests, and all of them shows that the DP can be extended longer than the martensitic. You can either look at its uniform elongation or the total elongation. Of course, such a advantage is very, very marginal. So of course, you cannot expect 10% ferrite to do better. And similar phenomenon we can also observe on the forming limit curves of these two materials. The DP shows slightly better formability, a higher formability curve than the martensitic. Of course, such advantage is very marginal. And this is exactly as we expected, again, because of the ferrite. This soft phase provide additional ductility or formability to the DP. But if we move on to local formability, we can see a different result, either in tension or Hooke expansion ratio or the VDA local bending angles. The martensitic shows higher values than the DP. And again, this is again caused by the softer face in the DP. Because of the soft and hard faces neighboring to each other, it's very likely that the micro voids can be nucleated between these two faces and eventually evolve to the final fractures. To support such a theory, basically we can see some fresh micrographs here, especially at the bottom. We can see on the DP 1470s fractured samples, we can see multiple microvoids happened basically on the boundaries between the ferrite and the martensite. And as a comparison on the top two pictures, we can see some microvoids in the martensitic 1500 caused by other mechanisms such as martensitic cracking, decohesion, or some inclusion particles. But none of these can be compared to the microhardness difference as shown in the bottom. So, and then we can move on to crashworthiness. Of course, this crashworthiness means some practical conditions into the testing, and it's actually the same concept as the local formability, but we basically generalize the local formability to local ductility, and the mechanism is still the same. The primary mechanism is caused by the microhardness between the hard and soft face. And of course, based on this mechanism, we can have the same conclusion like the previous section, which is the single phase should exhibit better than the dual phase. As for the testing procedures, here we added the rate dependency and also the stress state dependency into the testing. For the rate dependent tensile test on the left-hand side, the nominal strain rates we covered all the way from quasi-static to 1,000 per second. That covers the typical stamping and crushing strain rates. And on the right-hand side, for the stress state dependency, we basically tested 4 representative stress states, all the way from simple shear to uniaxial tension to plane strain to equiaxial tension. And based on the results, we can calibrate the modified Moore-Coulomb model to basically basically conclude the fracture loci of the two materials. And to be specific, let's start from rate-dependent tensile test. Let's first look at their stress strain curves at different strain rates. And again, left-hand side is martensitic, right-hand side is DP 1470, and both of them show some positive strain rate sensitivity on the hardening curves. And more important thing is at almost all the strain rates, if we look at no matter the uniform elongation or the total elongation, the DP shows better results than martensitic. This is consistent with what we saw in the previous quasi-static tensile tests. But if we move on to the fracture strain at different strain rates, again, we saw the consistent result, which is the martensitic shows better results than the DP. And here we can see some key points. First is that at quasi-static, because here we use the subside samples, we basically change the width to thickness to length ratios. We basically slightly change the track-static ratio. So maybe here the values are slightly lower than the fracture strain results we concluded based on the ASTM E8 samples, but not much. And then we see that when the strain rates goes faster, basically we see both of the material exhibit a decreasing trend with the increasing of the strain rate. And the mechanisms behind this is one, the positive rate-dependent hardening. That means the faster testing, the faster hardening. Fast hardening means the easier fracture happened. And also at this stage, the adiabatic heating start to play a role that basically brings the deformation and fracture happened in a certain temperature range, which is opposing to the fracture strength. And then the next one is that if we compare the two, the decreasing trend of the DP is slightly slower than the one of the martensitic because of the faster hardening rate of ferrite to the strand rates. But this kind of trend is not that significant, but we can still see some. And then after 10 per second, if we further elevate the strand rate, we'll see the recovery of the fracture strength of both materials. And this is because of the rapid adiabatic heating to basically brings the fracture happen in a fracture strength favoring zones. Of course, this kind of temperature dependency of the materials we have already have some results and we'll publish in the future. And of course, at all the strand rates, because of this, the softer phase in the DP, the fracture strength of the DP is not as good as the martensitic. And also, both of the materials exhibit some similar behavior that basically start from the high value and then go to a valley between 1 to 10 per second, then go back to 1,000. We can check the fracture morphology of both materials to see some kind of similarities between the materials. At the left-hand side, the two images basically at quasi-static strand rate. Both materials exhibit large effective fracture area. Basically, you can see the fracture area of both materials is very complex. That basically increase the fracture energy, and that also elevates the fracture strength. And in the middle two images, basically, we can see some kind of shear-like fracture, very smooth fracture surface of both materials happened at 10 per second. That corresponding to the lower fracture strength. On the right-hand side, we see this kind of complex fracture surface again, that basically corresponding to the recovery of the high fracture strength of both materials. And then if we move on to the stress state dependency, we tested other three loading conditions than the uniaxial tension, and then we can basically derive the fracture loci of both materials based on the MMC model. As we can see here, at all these stress states, basically the martensitic is better than the DP, again because of the micro hardness difference in the DP. And also this happened in all the four stress states. And to be more realistic, of course, we want to combine these stress dependency with strand rate dependency together, but that is something we're working on and will publish in the future. So as a summary, we can basically conclude this diagram here that the key point between the two material is whether it contains the soft phase, which is ferrite in this case. If the answer is yes, we can basically obtain some additional ductility stores to the global formability. But of course, if the answer is no, we have the single phase microstructure. We can see that the bake hardenability and the local formability, also local ductility, all elevated, and all of these can be basically validated by different testing results, as we listed on the right-hand side. And then we can move on to the second part. Basically, we would like to include also some two hot forming grades. The first hot forming grades, which is PHS, we'll talk about that in next slide. We'll skip that for now. And we here basically brings in the aluminum alloy 1775 T6, not only because of its absolute tensile strength, because it's only basically a 500 megapascal material, but we basically heard some theories that for these aluminum alloys, because of its basically the good basically strength to density ratio, it should be compensated by such a ratio, which is 3 compared to steels. So therefore, so its equivalent tensile strength should multiply by 3. So it's also a 1500 megapascal material eventually to be comparable with all the steels. As for the PHS 1500, it's very interesting and very complicated material because first, its microstructure keeps evolving, as we basically pointed out, that is basically started from ferritic to austenitic to fresh martensitic and then to tempered martensitic. So it deserves its own publications, and we basically have already published some work, and we will continue work on this specific grade in the near future. And also this material has its unique advantage, of course, when it's fully austenitized, it's basically very ductile. It almost have no spring back issues like the cold forming grades. But also this material has its kind of a unique problem, especially its aluminized silicon coating, which is a very brittle coating. And we have basically published some work showing that this brittle coating can bring early fracture to this material. And of course, these materials ductility can be yield strength and ductility can be further elevated after the baking or say the martensite tempering at all strain rates and all stress states. We have already have some relative publications in the GDIS in the past 2 years. Please feel free to refer to them. So if we put all the materials together in this study, we basically have all the cold rolled, uncoated, fully treated samples together. And here are the list of the testing we want to perform, especially to compare their ductilities. First, the bake hardenability, of course, this is not really a fair comparison, especially for the aluminum alloy 1775. Because for the aluminum alloy, these kind of pan baking cycles is typically integrated in its artificial aging process. But again, we just want to make them comparable with the steel, so put them together. And also for the hot forming grades, the dislocations generated during the pre-straining can hardly survive from the temperature. So that's why we basically excluded the pre-straining conditions. We only directly bake the samples and compare with their nominal states. And here we can see the stress strain curves on the left-hand side and their yield strength change after the baking. We can see because of the stress relief from the steels, we see large elevation on the yield strength, especially in martensitic. And for the aluminum alloy, it's already fully aged. And then if we further bake it, we're basically over aging the microstructure. We actually got softener. So we basically got softer materials. And then if we move on to the ductilities, and here left-hand side are the stress strain curves of the four materials. They don't really make practical meanings here. We just show them here for reference. As for the right-hand side, we can see the fracture strength of these four materials from the tensile samples. And here the PHS shows the highest values. This is because of the different carbon contents in the PHS compared to the martensitic grades. The lower carbons basically make the martensite of the PHS is slightly more ductile than martensitic, and such the fracture strength of the PHS can be further elevated if we bake it. And also here, the PHS we tested here is no coating type, so we don't have the negative effect by the coating. And for the DP, also basically the lowest among all the steels, and the aluminum alloy is the lowest in this aspect. And then if we add the rate dependency into the tensile test, we can first look at their stretch-on curves, that all the steels, all the three steels exhibit some positive hardening curves, basically. Comparatively for the aluminum alloy, basically, it doesn't show much change on the hardening with the strand rates. And if we plot their fracture strand fracture strand changing with the strand rates, we can see all the steels exhibit the similar trend, a ductility value between 1 to 10 per second. Again, the mechanism is already introduced in previous section. As for the aluminum alloy, because the hardening is not very sensitive to the strand rate, we can see its basic exhibit comparatively very consistent fracture strand along all the strand rates from slow to fast. And here we also want to basically check their local bendability based on the VDA bending standard, because based on some theories, some people believe that the local bendability can already represent the crashworthiness of materials in the real applications. And here, if we first check the conventional bending, local bending angles of all the four materials, basically the two martensite grades are very similar, and followed by the DP and aluminum alloy. And here, if we can basically deploy our 3D GDIS to measure the fracture strength happened on the bottom side of the bending sample. And of course, the detailed figure will publish next year. And we can basically conclude the fracture strength along the plane strength condition. Of course, here the deformation mode is out of plane deformation, and we can see the fracture strength based on the DIC results. This kind of rank is very similar to the bending angles on the left-hand side. And we can also test it, the stress state dependency on these four materials, and plot their fracture loci. And here again, we can see the two martensite grades are very similar, and followed by the DP and followed by the aluminum alloy. And here we would like to point out that the plane strength testing here, we used the in-plane notch tension samples. It's also a plane strength stress state. So compared to the fracture strength we obtained from the VDA local bending, which is out of plane fracture, the results are almost corresponding to each other, which is a good sign. So here is a brief summary of the second part. Basically, the two martensite grades, martensite 1500 and PHS 1500, shows similar ductility, but of course, because of the high residual stress in martensite 1500, it shows better bake hardenability on the tensile strength. And of course, because of the lower carbons in the PHS, it basically shows slightly better tensile fracture strength. And of course, for the PHS, its fracture strength can be further elevated if we temper this material. And aluminum alloy shows pretty good tensile elongations with or without the strand rates, but it doesn't really matter, basically, especially as we keep emphasized that the elongation cannot represent the fracture strength. So this is the results. And here we can conclude our presentation today. in the first part, we compared two cold-forming 1500 megapascal grades, martensitic versus DP. And one of them is fully martensitic, the other one is martensite plus 10% ferrite. And because of the ferrite, which is the soft phase, the DP 1470 exhibits lower bake hardenability, higher global formability, lower local formability, and the lower fracture strength, especially in the crash scenarios. And to some extent, if we just compare these two simple materials based on microstructure, we can basically postulate their mechanical performance. So here is a question: in the future, when we basically design the material, the new steels, whether we still go to the dual or multi-phase strategy, or we can think about the single phase strategy, microstructure strategy. And then in the second part, we also involved the two hot forming grades, one PHS, one aluminum alloy. And PHS 1500 is a very complex material, basically. But in the result, it exhibits similar fracture resistance compared to the martensitic 1500, also because of its lower carbon contents and more potential in the following pan baking treatment. So this material is also very promising in the applications. And of course, for us, the most important thing is that all the three studied ultra-high-strength steels exhibit much better fracture resistance than aluminum alloy 77.5 T6. And of course, for our customers in the future material selection, there are so many factors need to be considered. But as a material supplier, we can offer many options to our customers for their choice. So thank you everyone for your attendance. And for more information, please feel free to contact us or refer to our relative publications. And thank you.
Thanks, Jun.
Yeah.
Thank you very much for this insightful presentation. I think the question and answer panel is filling up real quick here.
All right,
so let's get to it. The first question here, I think, is asking, comparing the flatness of MS 1500 with DP 1470. I'm assuming flatness in terms of like a coil flatness. Any comment on that, or is that's beyond the scope of this?
No problem. Actually, our mills have the capability to flat both of these two materials, and I believe that's a reason why the residual stress in these two materials are higher than the PHS, and that's why when we bake them, we can see more elevation on the yield side. Basically, you can see the stretching curves and see the diagram on the right hand side, and we believe part of the residual stress were basically caused by the flattening.
No, the other question is how were the tensile tests performed at 1,000 strain rate?
How well? So basically, we have. I'm not very sure what that means. Like we have some tricks to basically surprise the ringing problems. So if you check the stress front curves, they look pretty good, I will say. I mean, we can see a little bit ringing issues. That's normal. And of course, maybe the paint will peel off a little bit near the fracture end. So maybe the end section is not very good. But I mean, based on the stress front curve, they look pretty good.
Well, no, I think Jun, the question is how the tensile tests were performed.
How they was performed.
Oh, yeah.
Okay. Sorry. Oh, okay. So basically, I'm not sure whether you can see my background. See me in my background. On my right-hand side, we have our high-speed hydraulic testing machine on the right-hand side. So the speed can goes all the way to 20 meters per second. And for the samples we use, the parallel gauge length is basically 15 millimeters. So at roughly 15 meters per second, we can already test the 1,000 per second.
Yeah. Great. Yep. Which one of these cold forming which one of the cold forming grades, I'm assuming the 1500 and the 1470, would be better in spring back?
Spring back wise, we didn't test them. We can test them if needed. I will say, I mean, based on their strength level, their result will be very similar, I will say.
Okay.
Very similar.
And then the same gentleman is asking, could you also explain more about what do you mean by local and global formability?
Sure. So basically, local formability, we can basically go to the corresponding slides here. So the global formability is what we typically use to represent the necking resistance, and the test results to basically represent these are like tensile elongations or forming limit curves, something like that. For the local formability, or say local ductility, it is a concept to represent the fracture resistance of the material. And in the testing results, we can basically see the local bendability, hole expansion ratios, and also the fracture strengths based on different methods. And of course, for more details to distinguish these two concepts, you can basically refer to Brandon Hahn's publications in the past few years. Also, we have already published some work.
Okay.
Thank you.
Another question, I think it kind of alludes to the fact that it seems like the 1470 might be a slight low performer. So are you working on a DP high ductility or a quenched and partitioned steel? I mean, is that in your portfolio?
I cannot talk too much about that, but I basically proposed the QNP 1500, but the problem is like QP has its advantage and disadvantage.
Yeah.
The biggest disadvantage is that QP process is comparatively very complex, and that complexity brings high cost and very hard quality control. So we have QNP 980 and 1180. 1500, it's hard to basically say whether we're going to develop that in the future. Maybe in the lab conditions, yes, but in mass production, I cannot talk about that too much.
No, understood. Yeah. Okay, so invariably you would get to the question about weldability. So have you compared the weldability of these grades?
To basically try to basically exclude these kind of concerns, all the materials we used in this study are basic uncoated ones. For uncoated materials, welding shouldn't be a problem. The coated versions, is too much to be squeezed in this study. And of course, but my colleagues, especially the welding expert, is working on it. And you will see more publications on the weldability of these materials in the near future.
Can you elaborate a little bit more on the mechanism behind the slightly elevated localized formability of the fully martensitic 1500 over the DP material? I think you alluded to that in one of your slides. Yes.
I'm assuming you're talking about these kind of explanations here.
The fact that the local formability of the 1500, the MS 1500, is much better, or is better. Just the mechanism.
Yeah. So the mechanism is not single, but based on the representative based on the representative literatures I basically listed here, you can refer to these representative literatures, and basically the common conclusion from them is that the soft and hard faces neighboring to each other, the micro hardness basically is enlarged, and that can easily cause the micro voids, and the micro voids can eventually evolve to fracture. Basically, we can see this micrograph here.
Yeah,
and
yeah.
yeah.
Excellent. So the homogeneity of the material actually is the one that actually helps with the local formability.
Of course, of course.
So there is another question. When you conducted the bake hardening tests, have you seen any abnormal fracture at the transition area, not at the gauge length, on the MS 1500 or DP 1470 tensile specimens at higher pre-strain? If yes, yeah, the rest of the question is if yes, what would be the root cause?
The issue of the bake hardening testing is that for the samples, like when we pre-strand them, and the shoulder area will basically less pre-strand, and the parallel area is fully pre-strand, and then we bake them. The shoulder area basically with less pre-strand were basically hardened less, and the gauge area, which was fully pre-strand, were basically fully hardened. And then when we pull them in reloading, it's very likely that the hardness of the gauge area is higher than the shoulder area. So if we pull it, the fracture could happen from the shoulder area, which basically not a good thing. So our method, and also many other colleagues' method, is basically we don't cut the dog bones directly. We basically cut some kind of the stripes, and we pre-strand the stripes. First bake the stripes, and then we machine the dog bones before we reload them to fracture. That could help the fracture basically happen in the gauge area rather than from the shoulder area.
Very good.
Yep.
Very good. Thanks.
Yep.
What do you consider to be the highest tensile strength in megapascals that steel can be practically cold or roll formed?
I mean, in the literature, if it's beyond automotive, I saw 3 gigapascal steels, but that's not sheet steels. Sheet steels, what already commercialized is 2000 megapascal.
Yeah.
Yeah.
What's an acceptable bending angle for various applications?
That depends on our customers' specs, and also, yeah, especially our customers' specs. It's basically, I would say depends. Some of them basically say minimum 45. Some of them say minimum 42, and yeah, roughly for 1500, maybe 40 or 45 minimum is a baseline.
Okay.
Yeah.
Another question, which is, it says, what is the initial condition of martensitic 1500? How you get good ductility? Any microstructure modifications with tempering?
Yes, these martensitic grids were already, both the DP and martensitic grids are already tempered during the processing. So okay. Yeah, so compared to the PHS here, the PHS here are basically as quenched condition. And for the martensitic 1500 DP 1470, the martensite are basically already tempered during the production.
Okay. Another question asking about the gauge ranges that these two, the 1500 and 1470, are available in.
Yeah, please check our website or basically contact our application engineer group.
Very good. Yep. Very good. Yeah. How do you achieve fully martensitic microstructure in the production process in the mill? Do you have a water quenching process at the end of the annealing process?
You mean the martensite and the DPs? Yes, of course.
Yeah, it says how do you achieve a fully martensitic microstructure in the production process? I'm not quite sure. Is that the MS or the PHS? But
yeah, PHS. PHS basically I mean only our like tubular component company do the water or oil quench. Otherwise, we produce the pre-quenched PHS coils to our customers. Martensitic and DPs, yes, we have quenching set up in our production lines.
okay, I
Yep.
think we can take one more, and then unfortunately we'll have to kind of ask the rest to maybe communicate with you via email. But one more question here. Can you comment further on the fact that the strain fracture in plane strain tension and bending are the same? As you mentioned, plane strain tension undergoes in plane deformation, while bending is out of plane deformation. So what is the effect of in plane or out of plane deformation on the fracture mode?
Yeah, that's basically the beauty of using the DIC, because we can basically plot the strand path based on the DIC measurement results. And here I don't have the plots of the two, but if you plot them, if you have a DIC, you can basically plot the strand path of the two. Basically, no matter the in-plane or out-of-plane plane strand test, you will see kind of a the strand path basically along the traxiality ratio near to the 0.577, which is plane strand of both of them. No matter it's in plane or out of plane, you will see the strand path.
Okay.
Yep.
All right. Well, I believe if Brian would allow us, we can have one more. It says, can you briefly touch touch on the reason why you have fracture strain softening at 1 and 10 per second, and then it is increasing at the higher strain at 100 and 1000?
Sure. So let me jump to that slide pretty quickly here. So as I basically indicated here, there are two mechanisms, we believe. One of them is the positive strain rate dependency on the hardening of the steels, because if you see their stress strain curves, when the strain rate is elevated, the hardening basically goes higher, which means the faster testing, the faster hardening. The fast hardening means the quicker fracture happened, and that basically lowers down the fracture strain result in this region. And also rate dependent test is never purely rate dependent test. We have to consider the adiabatic heating, we have to consider the temperature dependency of the two materials, and based on our temperature dependent tests, we basically got recently that the sensitivity of these two materials on the fracture strength is not basically linear to the temperatures. In certain temperature range, it's very opposing to the fracture strength. And we believe that opposing temperature range is caused by these 1 to 10 per second. Very likely. We don't have the high-speed thermal camera to verify that, but we believe that's roughly the temperature range to basically decrease the fracture strength around these strain rate. As for the recovery of the fracture strength, when we goes to faster speed, and again, it's basically related to the temperature sensitivity of the materials, and based on our tests, at certain temperature range, the fracture strength can be boosted by the temperature. And we'll also publish that results probably next year. Long story short, during these strain rates, rapid adiabatic heating can elevate the fracture happened and can basically elevate the fracture strength. and that, yeah. So that, I guess that explains your question.
Okay, interestingly enough, staying on this slide, there was a question relative to the fracture strain values on the y-axis here. The question is, are they so? Why are they so high, or are they so high? I don't understand exactly what is meant by the question, but I think the comment is on the values of the strain,
Sure.
fracture strain on the y-axis.
Sure. So single, I mean, not only single, I will say, like, based on our hybrid method, these two materials basically shows these values, not very surprising, and depends on which method you use to derive the fracture strength. If you use pure DIC value, DIC measurement, you'll probably see, like, for example, 0.4, 0.3 fracture strength. But again, based on our publication in the past 2 years, that's not true, because DIC measurement, you have to use the volume constancy assumption to basically derive the thickness strength, and that's not accurate. And if you use basically purely optical measurements like area reduction, you also have to use the volume constancy assumption. That is also cause the deviation. Yeah.
I'm afraid that Brian raised his hand here, so I'm afraid everybody else, I didn't get to your questions. You could correspond directly with Dr. Hu at Cleveland Cliffs. I'll return back to Brian. Thank you very much, Jun. This was really insightful, and I think a lot of people are interested in it.
Yeah, thank you. Thank you.
Thanks, Hisham. Jun, thank you so much, Dr. Hu, for a really insightful presentation. And wow, what a Q&A. We had more than 35 questions there. I know you couldn't get to them all, but thank you both for your time and taking us through that. Just as a reminder, thanks to all that joined us. Our copy of the recording of this presentation, as well as the slides, will both be available on demand at our website, autosteel.org. and also through the greatdesignsinsteel.com website. Just as a reminder, upcoming GDIS technical webinars, the next two on artificial intelligence, including AI and steelmaking, and as well as vehicle optimization. You can register at autosteel.org and watch for additional webinars to be announced. Save the date for our annual Great Designs in Steel Symposium, May 20th, 2026. Details will be available at the website. And lastly, next week, we open our call for abstracts for speakers for the symposium. You can submit your abstracts at greatdesignsinsteel.com. Thank you again to everyone for joining us, and have a great day.
Thank you.